Welcome back to Let's Learn Calculus. Today we're just going to be doing a quick introduction to calculus. So recall that in section 2, we discussed average slope or the average rate of change. This allowed us to answer questions such as, if a car's position is given by p of t is equal to 2t squared plus 3, on average, how fast is the car moving between t equals 5 and t equals 10? The solution would just be the average rate of change. So we look for the average rate of change, which is p of 10 minus p of 5, divided by 10 minus 5, which just simplifies down to 30. But what happens if we wanted to know how fast the car was going when t equals 5? Well, if we tried to use the average rate of change formula, we would end up with 0 over 0. And this is what we call an indeterminate form, which at this point in time doesn't do us a lot of good. So how can we remedy this? Well, the possibility 1 is to create a table around 5. So we're going to look at t values of 4.9, 4.99, 5.01, and 5.1. And we know that at 5, we're that indeterminate form 0 divided by 0. If we look at 4.9, we get 19.8. If we look at 4.99, we get 19.98. If we look at 5.01, we get 20.02. And if we look at 5.1, we get 20.2. That'll leave us to conclude that maybe as t gets closer to 5, the average rate of change gets closer to 20, meaning that when t is equal to 5, the instantaneous rate of change is equal to 20. But what's wrong with doing the table is that we're still some distance away. We're not exactly at 5, we just keep getting closer and closer to 5. So our second possibility is what finds some value L, so that whenever t is close to 5, the average rate of change is close to L. And I know that sounds a little confusing, we'll try to clear it up here. So the definition of a limit. From the last slide, we wish to reformulate what was said that we want to find a value L, so that whenever x is close to x naught, f of x is close to L. Well, this gives us a definition of a limit. So the limit as x approaches x naught is the value L, so that for all epsilon greater than 0, there exists a delta greater than 0, so that the absolute value of f of x minus L is less than epsilon whenever the absolute value of x minus x naught is between 0 and delta. Notice what this is saying. This is saying that whenever x is close to x naught within delta of x naught, that we have f of x is close to L, that is, within epsilon of L. And we denote this by writing the limit as x goes to x naught of f of x is equal to L. So how does this help us? Well, remember what we're trying to do. We were trying to find a value L so that whenever t is close to 5, the average rate of change was close to L. The first is close can be replaced with t minus 5 less than delta. So we want t minus 5 to be less than delta, which means t is pretty close to 5, and the second is close to gets replaced with the average rate of change minus L is less than epsilon. That means that the average rate of change is close to L. And that's going to do it for this video. Hope you guys liked it. If you have any questions, feel free to leave them in the comments, and be sure to follow me on Instagram and Twitter, and I'll see you guys in the next one.